Hey everyone, let's do a quick experiment. Just look around you, right now. See the air you're breathing? Well, you can't see it, but you know it's there. And the phone or computer you're watching this on, what do they both have in common? It's a super basic question, right? But the answer is, well, it's everything. Today, we're diving deep into the science of all the stuff in the universe. We're talking about matter.
So yeah, really think about it for a second. You've got air, which is invisible. You've got water, which you can pour. And you've got your phone, which is totally solid. I mean, they couldn't seem more different, could they? But underneath it all, they share this one amazing secret. So what is it? What are they all made of?
Boom, you got it. It's matter. And if you were thinking that, you absolutely nailed it. Now the definition sounds kinda textbooky, right? Anything that has mass and occupies space. But let's break that down. Mass is just a fancy word for how much stuff is packed into an object. And occupies space? That just means it takes up room. It has a volume. So if it has stuff and it takes up space, congratulations, it's matter. We're talking everything from a tiny speck of dust to the biggest star in the galaxy. It's all just matter.
All right, so we know everything is matter, but what is the matter itself made of? What's the next level down? Well, this is where it gets really cool. Imagine we had a super-powered microscope and could just zoom in and in and in, way past anything we can see with our eyes. What we'd find is a whole secret world. So let's go. Let's dive in and see what matter is really made of. Okay, first big secret about these particles. They're not all squished together like bricks in a wall. Nope. There are actually tiny little gaps or spaces between every single one of them. You've seen this happen, I promise. Ever stir salt or sugar into water? Where does it go? It looks like it just disappears, right? But it doesn't. What's really happening is the tiny little salt particles are just finding and filling in all the empty spaces between the water particles. It's kind of like they're grabbing the last few empty seats in a packed movie theater. So clever. Secret number 2 is even wilder. These particles, they never stop moving, ever. They are constantly jiggling, vibrating, and bouncing around like they've had way too much coffee. This nonstop motion is called kinetic energy. And you've experienced this too. Think about it. How can you smell a pizza cooking from all the way in the other room? It's because those delicious pizza smell particles are literally flying through the air, bouncing off everything in their path on a mission to get to your nose. It's a constant, invisible dance happening all around us.
And for our third and final secret, with all that bouncing around, why doesn't everything just fly apart? Well, it's because these particles also attract each other. There's this force, kind of like they're all tiny little magnets, pulling them together. This force is what gives stuff its structure. In something solid, like a chunk of iron, that force is super, super strong, holding all the particles in a tight grip. But, and this is the important part, that force isn't the same for everything. And that one little fact explains, well, a whole lot.
Okay, so let's put it all together. Think about water. You can have ice, which is solid, you can have water, which is liquid, and you can have steam, which is a gas. But they're all made of the exact same stuff, water particles. So what gives? Why are they so incredibly different? Well, it all comes down to a battle. A battle between that let's fly apart kinetic energy and that let's stick together force of attraction. And this chart right here is like the scorecard for that battle. Let's look at solids. See that force of attraction? It's at maximum. The stick-together force wins, big time. The particles are locked into a grid they can only vibrate. That's why a solid has a fixed shape. But now check out liquids. The attraction is weaker, intermediate. The particles have enough energy to break free and slide past each other. So the stick-together force is strong enough to keep them in one group, giving it a definite volume, but not strong enough to hold a shake. And then you get to gases. The force of attraction is basically non-existent, and kinetic energy is at a maximum. The fly-apart energy wins completely. The particles are just zooming everywhere, which is why a gas will fill up any container you put it in, no matter how big.
So here's where we get to play mad scientist, because these states, solid, liquid, gas, they aren't set in stone. We can actually force them to change. We can make a solid turn into a liquid, or a liquid turn into a gas. And how do we do that? We rig the battle. We change the balance. And the easiest way to do that is by adding or taking away heat, which is just another way of saying we're adding or taking away particle energy.
This diagram is basically our map for changing states. The ones we all know are here. You add heat to a solid, you get melting. You add heat to a liquid, you get vaporization or boiling. And you can go backwards too, by cooling things down. But check out this cool shortcut down at the bottom, sublimation. This is the really weird one, where a solid just says, nah, I'm skipping the liquid phase and turns straight into a gas.
You've seen this with dry ice, that awesome spooky fog effect? That's solid carbon dioxide sublimating right into gas.
Okay, get ready for a bit of a brain bender. Let's say you're melting a glass of ice. You put a thermometer in it, and as long as there's still ice, that thermometer will read exactly 0 degrees Celsius, even if you keep adding heat. So, where is all that extra heat going? It's not raising the temperature. Well, that energy is on a secret mission. Its job isn't to make the particles move faster. Its job is to break the bonds holding them in that solid ice structure. This is what we call latent heat. It's the hidden heat that's busy changing the state, not the temperature. So, this whole idea of hidden heat isn't just a weird science fact. It actually explains something really serious and something you need to be careful about. Here's the puzzle. Both boiling water and the steam coming off it are at the exact same temperature, 100 degrees Celsius. So why then is a burn from steam so much worse? The clue, as you might have guessed, is all about that hidden energy.
The number is just huge. For every kilogram of water that turns into steam, it has to absorb an extra 2,260 kilojoules of this hidden energy. So when that steam hits your skin, you get a double whammy. First, you get the burn from the 100-degree temperature. But then, the steam instantly condenses back into water right on your skin, and it dumps that entire massive payload of hidden energy all at once. That's the extra kick that makes steam burns so incredibly severe.
Okay, so we've been talking about boiling, which is a really dramatic way for a liquid to become a gas. But it's not the only way. There's a much quieter, slower, and honestly, way more common process that's happening literally all around us all the time. Let's talk about the magic of evaporation.
Now, it's super important to get this straight. Evaporation is not the same thing as boiling. Boiling is like a rock concert. It's loud, it's fast, there are bubbles everywhere, and it only happens at one specific temperature. Evaporation, on the other hand, is like background music. It's a slow, quiet process that only happens at the surface of the liquid. And the cool thing is, it can happen at pretty much any temperature. You know when you see a puddle slowly disappear on the pavement, even on a cool day? That's not boiling, that's evaporation in action.
And just like a video game, they are cheat codes to speed up evaporation. We use them all the time without even thinking about it. You want your clothes to dry faster? You spread them out, right? That increases the surface area. You know they dry faster on a hot, sunny day than a cold one. That's increasing the temperature. And why do they take forever to dry on a humid, rainy day? Because the air is already full of water, so there's no room for more to escape. And of course, a windy day helps a ton, because the wind just whisks the escaping water particles away. See? You're already an expert at this.
But here it is, the single most important, most useful thing to know about evaporation. Are you ready? Evaporation causes cooling. It's a fundamental rule. But why? Well, think about all those particles jiggling around at the surface. Which ones are going to escape? Only the ones with the most energy, the fastest, hottest ones. And when they leave, they take all that energy with them. So what's left behind? The slower, less energetic, cooler particles. The average energy goes down, which means the temperature drops. This is literally how your body's air conditioning works. When you sweat, the evaporation of that sweat is what pulls heat away from your skin and cools you down.
All right, that brings us to one final brain teaser to see if you've got it. We all know a fan doesn't actually make the air in a room colder, right? It's not an air conditioner. It just blows the same warm air around. So, why does it feel so amazing when you stand in front of one on a hot day? The answer combines everything we just learned about moving particles and, most importantly, evaporation. So think it over. When you figure it out, you'll realize you're a master of the physics of cooling. Thanks so much for hanging out and exploring the amazing world of matter with me today.